welcome back, AP Calc. Are you ready for logarithmic differentiation? This is section 5.1. We're on our last two examples. So we are going to use our properties of logarithms in order to differentiate a complex problem. So number 9 up here is a nice quotient, but within the quotient you have a product, and then you get your power down on the denominator here, and this is just a whole bunch of a mess if I wanted to take the derivative of this y equals function using the quotient rule. And of course we have an embedded product rule up in there, not to mention that square root sign, which will give us 1/2 x to the negative 1/2 or something funky like that. So we're going to use logarithmic differentiation in order to do this. Logarithmic differentiation is when you introduce the natural log. Notice there's no natural log in this problem at all. So I'm going to introduce a natural log. This is going to say natural log of y is equal to the natural log of this whole stuff, this big mess up here. 3x squared times the square root of 7x cubed minus 2x all over the quantity of 4x minus 1 cubed. So now I'm going to use my properties of logarithms, and I'm going to break this power up into a whole bunch of different little pieces. Natural log of y, I'm just copying, I'm not differentiating yet. You have to first put your natural log in both sides and then use your properties of logarithms. So this becomes natural log of 3x squared plus 1/2 times the natural log, and I think I'll write my 1/2 with a loop to make sure. Natural log of 7x cubed minus 2x. Okay, because this quantity right here was really to the 1/2 exponent. But I took that 1/2 exponent and I brought it over as a leading coefficient because I have a property of logarithms that allows me to do that. Now the division is going on with my powers here, so I'm going to subtract my exponents. Each of these logarithms is an individual exponent. And this gives me, and I'll leave a space here because I'm going to do that same thing again, 4x minus 1 quantity cubed, but I'm going to take that 3 and I'm going to bring it right here as a great big coefficient and erase it, and pretend like I did that right from the beginning. How's that sound? And now I think I'm ready to go ahead and differentiate. The derivative of the natural log of y is 1 over y dy dx. The derivative of the natural log of 3x squared is going to be a fraction with whatever the natural log is applied to on my denominator, and then this derivative goes on the numerator, so 6x on the numerator, plus 1/2 times the 1/2 I just carry, it's a constant, a fraction again, whatever my u is here. This is 7x cubed minus 2x, and this derivative goes on the numerator, 21x squared minus 2, and then the minus sign is copied, the 3 is copied, and we have another fraction here. Whatever the natural log is applied to goes on the denominator, and this derivative goes on the numerator. Now I just need to neaten this up just a little bit. I have 1 over y dy dx. Notice this is not solved for dy dx right here, so I'm going to have to manipulate that in just a minute. 6x over 3x squared reduces down to 2 over x, right? 3 goes into 6 twice, and I have an extra x in the denominator. Plus, this 2 does not divide off with anything, so my numerator will still continue to be 21x squared minus 2. And just because I can, I'll factor an x out of this little piece, this factor. And when I take this x out, I'll have 7x squared minus 2. And nothing can divide off here, so 3 times 4 makes 12 over 4x minus 1. I'm almost finished. I just need to get rid of this y right here. So what I'm going to do is I'm going to multiply the left side of the equation by y, and I'm going to multiply the right-hand side of the equation by y. This will divide off, and I'll just have dy dx. Now, I'm going to write this y first, if you don't mind. However, I'm not going to write the letter y. I'm going to go back up into my given problem, and y in terms of x was this whole mess. So I'm going to copy that whole mess, 3x squared times the square root of 7x cubed minus 2x all over 4x minus 1 quantity cubed. This is my y. And then I have this whole other thing here, which I'm just going to copy, 2 over x plus 21x squared minus 2 over 2x times 7x squared minus 2. And then minus the last fraction is 12 over 4x minus 1. Again, this y was brought way over here. So I'm finished. This is my dydx. I could, of course, go a little further, form a common denominator, get these 3 fractions into 1 fraction. But as far as I'm concerned, I wanted to see that you understood, number 1, that you needed to apply logarithmic differentiation to get the job done faster. You applied the natural log on both sides. You'd used your properties to split up the right-hand side of your equation. And then you differentiated, and I wanted to see each one of your steps. So I'm fine with this being complete right here. Okay? So that would be question number 9. Question number 10 is actually example number 6 from page 319 in your book. So the book does a pretty good job of explaining how to get the final answer, but there's a little bit of ambiguity in the middle someplace, so I'm hoping I'm going to explain it all a little bit better for you. So we're looking at y equals x minus 2 quantity squared divided by the square root of x squared plus 1. Now I know that you can take this derivative just like it is. You could do the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. However, this derivative of the bottom is going to give you a complex fraction because you'll have a little fraction in your numerator, and that won't be very pretty. So I think logarithmic differentiation would be ideal for this problem. I can apply the natural log to both sides of the equation, and then I can use my properties to break this thing up and have a bunch of little natural logs to take my derivative of, and it'll be a nice and easy problem work. Now, in the book it says x does not equal 2. And the reason x cannot equal 2 is because this quantity is not allowed to equal 0. We'll talk about that as soon as I get my natural log brought in here. So let's go ahead and put my natural log of y is equal to natural log of, and it's this whole quantity, x minus 2 quantity squared over, and I think I would like to have that written as a 1/2 exponent, if you don't mind. Now the natural log function itself, if you recall what it looks like this. Goes through the point 1, 0, and this is y equals natural log of x. So this x value here is not allowed to be negative, and it's not allowed to be 0. So the x value itself has got to be positive, which is greater than 0. So that means that this whole power that's sitting inside here, which is like this x right here, has got to be greater than 0. Well, it has no chance of being less than 0, not with all these squares going on. I don't care what you have, you square it, and the thing is going to turn positive, unless, of course, it's a 0. You square a 0, you get 0. I mean, I don't care what number you take for x either. You square it and add 1, you get a positive result from that, and the square root of a positive result is another positive result. So the only thing that's even possible would be getting a 0 for my x. The only number that would make a 0 happen here would be that 2. So that's why in the original question they said, hey, I don't want x to equal to 2. And that's kind of a hint that they expect you to go ahead and do that logarithmic differentiation. All right, but that whole restriction is due on the domain of the natural log function having to not be negative and not be 0. This will never be negative, and the only one case in which it would be a 0 is if x were a 2. So we're saying, okay, it's not that either. All right. So I'm going to use my properties here for natural log. Natural log of y is equal to the natural log of x minus 2, quantity squared. And then minus natural log of x squared plus 1 to the 1/2. I'm going to continue using my properties of logarithms now and take these exponents down and write them as leading coefficients outside my logarithms. So this 2 is going to come down, become natural log of x minus 2. Minus 1/2 comes down, 1/2 natural log of the quantity of x squared plus 1. And I'm pretty much set now to go ahead and take a derivative. So the derivative of the natural log of y is 1 over y times dy dx. This is my chain rule here. Okay, if I felt like it, I could write this as y on the bottom and a y prime on top. I favor the dy dx. I like it better than the y prime, so I choose to use it. Equals, the 2 is copied, and now I need the derivative of the natural log of x minus 2, which puts whatever the natural log is being applied to on the denominator. And what is the derivative of x minus 2? Just plain old 1 goes on the numerator. Minus the 1/2, another fraction coming up, and the derivative of the natural log of x squared plus 1 is going to take the x squared plus 1, put it into the denominator, x squared plus 1, and the derivative of x squared plus 1 goes up on my numerator, 2x. Put the denominator down first, and then look at the denominator to take its derivative to throw it up on the numerator. Don't look back at the original function. And one of the things I really like about natural log, first off, natural log is pretty easy to write, but when I take the derivative of a logarithm, I don't have that logarithm involved anymore. So it's really kind of neat. I get rid of that natural log. Okay, so this is 1 over y dy dx. Don't forget, we're going to play with that in a minute. Equals, this 2 is going to stay here over x minus 2. I'm going to leave a little bit of a space here because I know what's coming up. I'm going to have to form a common denominator, and I want to have room to do so. So this is x squared plus 1 on this denominator. My 2's are going to divide off, and I'm going to have an x. So the common denominator that I'm looking for has to be with these two denominators. These two have nothing in common, so therefore we multiply the denominators together to get a common denominator. X minus 2 times x squared plus 1. And in order to build an x minus 2 into this new denominator, I'm going to have to multiply it by x squared plus 1. So I wrap it in parentheses, and I write x squared plus 1. And that will build my common denominator. But what I do to the denominator of a fraction, I must do identically to the numerator. Okay, x squared plus 1 over x squared plus 1 is really the number 1. So I'm changing the appearance of this fraction without changing its value. Anything times 1 is itself. And over here, I have the x squared minus 1. I'm missing the x minus 2. So I am going to multiply the denominator by x minus 2. But what I do on the numerator, on the denominator, I must mimic on my numerator as well. So distribute, multiply this out. This is 2x squared plus 2. This negative is going to go with this x, and both of them get distributed over the x minus 2. So I end up with a negative x squared, and now plus 2x. And this is still 1 over y dy dx. So I'm going to take this, and I'm going to come over here. 1 over y dy dx is now equal to one fraction. Okay, I'm going to leave a space because I know my y is going to go right there in a second. X minus 2 on the denominator, as well as x squared plus 1 on my denominator. And on the numerator, 2x squared minus x squared is just an x squared, plus 2x, and then plus 2. And I know that my 2's sometimes look like z's. Don't ever forget though, when I write a z, there's always a bar in the middle, okay? So if I see a 2 or if I see a 2, those are both 2's. The z was on has the bar across it. Okay, so far so good. My dy dx is now, I'm going to multiply both sides of the equation by y, so my y will come here, and I'll have x squared plus 2x plus 2 over x minus 2, x squared plus 1. Again. And now this y, I'm going to put the original function that was equal to y back in here, which is x minus 2 quantity squared over the square root of x squared plus 1. And this all gets multiplied by what's in these brackets. So I'm going to use a big set of parentheses though, if you don't mind, because there's, yeah, I use brackets. It's all good. X squared plus 2x plus 2 over the quantity of x minus 2 times the quantity of x squared plus 1. Now if you notice, you have an x minus 2 quantity squared on the numerator, and you have an x minus 2 to the first down in the denominator. So one of these factors can cancel off top and bottom, and I will just be left with an x minus 2 quantity to the first on the numerator. Still have this trinomial, which does not factor. And on the denominator, I have an x squared plus 1, and I'm going to write this as a 1/2. And I have an x squared plus 1 again. And this is just to the first power, so I can leave it as a first power, but I'm going to write it as 2 over 2 because I plan on putting those together. My dydx follows here. And my final answer is going to be dydx is equal to x minus 2 x squared plus 2x plus 2 all over x squared plus 1 quantity to the 3/2. All right? And I do believe that is what the book tells you the answer is. And on both of these, we now have a dydx, which is a formula that can find the slope of the tangent line given any x value. And if I gave you an x value, if I said, let's say x equals 1, you could go ahead and plug a 1 in here for x, and that would give you the slope of the tangent line at x equals 1. You could take that 1, put that back into the original function. That would give you the y value at x equals 1, which would yield an xy coordinate pair. You would then have a point and a slope, and you could use your point-slope formula to actually write the equation of the tangent line at any given x value using your slope formula. Okay? I think that's it. I hope that wraps things up for you, and we'll practice a little bit more tomorrow. All right? Talent out. Bye-bye.